Hi folks, it's our pleasure today to have with us Professor Aditya Akela from the University of Wisconsin at Madison. Aditya got his PhD at Carnegie Mellon University, where he also received the IBM PhD fellowship, and after that he joined Wisconsin, where he is an associate professor at the Computer Sciences Department. And Aditya's general area of interest is network systems, and in particular he's been working recently on content-aware networking. And he's been very successful, several papers in SIGCOMM and SDI in that kind of venue. And he's also received several best paper awards, as well as awards such as the NSF Career Award, Future Internet Architecture Grant, NetApp Faculty Fellowship. Please welcome Professor Aditya Akela.
So thank you for giving me this chance. I wanted to use this talk as an opportunity to describe work we've been doing over the past 6 or 7 years, and this is work that encompasses a couple of PhD theses and a couple of master's theses, and it's in the general area of content-aware networking. And so I want to tell you, what this is, why it is interesting, what doing research in this area entails, and how to approach it, and how we approached it, specifically using an example. So let me start by describing the motivation for this work, and feel free to interrupt me at any point during this talk if something is not clear. So let's go back to the start of time, right? So the original internet and its protocols were basically designed to connect up hosts. The idea was to get a bunch of hosts to talk to each other and have that communication between those hosts and entities on those hosts be resilient to attacks or partitions and so on. So this notion of hosts being the central point of communication actually runs pretty deep into our protocols and applications today. So for example, if you look at IP routing, it works on the basis of locations of hosts. If you look at TCP connections, these are pipelines between application endpoints, but really those connections are also bound to host addresses. If you look at URLs that we use ubiquitously to label resources on the internet, they again encode host names. So it's fair to say that the original internet, as it started out, was designed to be host-centric, and it continues to be that way today. Wherever we see it, the evidence is pretty clear. So this talk and my work in this space arises from the observation that it's time to revisit the host centricity of the internet, and I'm not alone in this. A lot of people have made similar observations, including Van Jacobson, who's worked on CCM. You're probably all familiar with. People like Scott Schenker, who's worked on data-oriented network architecture, you're all familiar with. And so basically, it's time to revisit this because if you look at the internet today, it's no longer about connecting hosts, right? It's about accessing content, accessing news services, and that's the predominant use case. It's more clear day by day that content, as opposed to hosts, has become an equal first-order entity, if not more of an important first-order entity than hosts on the internet today. So essentially, what we have ended up with is trying to realize content-oriented primitives like retrieving content, accessing content, or searching for content, or looking for services that will provide you content on top of a bed of protocols and infrastructure that is primarily host-centric. So this is a mismatch, right? So your intent is all about content, and what we have underneath is all about hosts. So why is this kind of mismatch bad? Well, it's bad because there are various things that can go wrong, but really it can lead to a lot of architectural consequences. For lack of a better word, you can kind of think of it this way. And what this essentially means is that some very important things that you care about for your high-level communication become unnecessarily hard to attain. So let's start with the simple things like performance. Right? You care about getting things that content that you care about in the most timely fashion. Often, because the network doesn't pay attention to the content that you're accessing, it's more about the host. The network ends up carrying the same byte repeatedly, and this impacts potentially the bandwidth you can get or the latency with which you can access that content. That's the simplest example, but there are other implications for this mismatch among things like security and authenticity for data and availability. So, for example, in terms of security and authenticity, users often would like to know that their data came from an appropriate source rather than some spoofing adversary. And today, obtaining these kinds of guarantees requires something like a global PKI to provide users with the public keys for the provider of the content. And moreover, if you look at how authenticity is obtained today, it's typically done by securing the channel between hosts as opposed to ingraining that within the content itself. And similarly, in terms of availability or achieving reliability, there are a lot of different issues that may arise because users are often the mechanisms that are used to achieve availability are sort of very application specific, and there's sort of no common reuse that you can see happening across applications. So what applies in one situation may not get to the necessary availability or reliability in another situation. So content-aware networking is sort of a relatively new line of research, relatively new speaking with respect to the 40 years of internet research, where the goal is basically to elevate content processing as a more of a first-order entity within network infrastructure and protocols. And there are various ways of looking at it, and I'm going to talk about that briefly. But the key advantage of elevating content to a first-order entity alongside hosts is that all these aspects that I talked about on the previous slide, performance and the need for security and authenticity and availability, become clear, and sort of they become consequences of your design choices and stuff. So performance, for example, by using content-aware networking principles, you can imagine making more efficient use of the network. Security and authenticity properties can be derived from the content itself, as opposed to relying on some out-of-band, PKI infrastructure. And availability guarantees for content can also be provided with support for with intrinsic support for mechanisms such as any casting for content, as opposed to having specific mechanisms that ensure availability for specific application scenarios. So content-aware networking sort of immediately addresses a bunch of these issues that arise due to host centricity, but it also can lead to the design of improved applications. In a network that is content-aware, you can have applications that work better than they work today. It can also give rise to new and hitherto unknown, unseen applications that have important new benefits that are simply not possible today. So some of the work that you're probably familiar with includes things like content-centric networking from WAN Jacobson, and they take more of a greenfield or clean slate view of content networking. But what I'm going to talk about today in this talk is sort of more of sort of interesting issues that you can address more immediately in the internet today and bring immediate benefit to applications and to users by leveraging content-aware networking. So let me, so with that setup on sort of what content-aware networking does, let me delve into sort of the three main strands of research I see in this space. The first, of course, is the one that comes to mind most immediately is how do you provide fast and cost-effective support for content processing inside the network. So if you look at a router or any sort of fast network appliance that exists today, it is very effective at looking up a packet's header fields and doing next hop lookups and so on. And we are talking about the equivalent of that in the content world, looking at some request for content or something about an attribute for content really quickly and figuring out what to do with it. and sort of in designing support for this kind of actions to work in a fast manner, a fast effective manner, there are a variety of tricks that you can dig into. So one of the things that ends up becoming important is something called content fingerprinting. This is something I'll touch upon in a slightly more detail later in this talk. And this is essentially being able to get some hooks into the content based on which you can do some further processing on the content. And careful choice of these content fingerprinting algorithms can lead to enormous benefits. Another set of tricks that we have applied and others have looked at in supporting content processing in a fast and cost-effective manner is to look for new technologies. So, for example, traditional IP tables and other lookup tables have been constrained to be situated within SRAMs or maybe DRAMs or TRAMs and sort of a specific kind of memory technologies. But with content, given the fact that the scale is larger, you would probably have to look at new technologies and how to leverage them more effectively, like things like solid-state drives or phase change memories or whatever else. And the last trick that is useful to do fast and cost-effective in-network processing, again, this is something I'll touch upon later in this talk with a specific example, is carefully dividing labor. And again, this is something that arises in the context of content processing, not so much in processing host identifiers, mainly because processing content in the network at fast speeds is hard because there is a lot more to do with content. So you gain a lot by splitting the work into small tasks and distributing that across multiple nodes and having them coordinate what they do to content. And using these kinds of tricks, sort of you can think of this as a small bag of tricks that we combinatorially combine and try to get interesting results out of. We've designed sort of a really fast packet level redundancy elimination scheme for routers, large hash tables that can support extremely large content indexes that can, for example, be used with deduplication mechanisms, video caches at large scales, and so on. So that's the first strand of research: how to build fast in-network content processing. And again, I'll touch upon this later in this talk. The second one is probably a little more disruptive, and it's mainly about where do you put these content-aware schemes. Do you situate them in the application layer? And do you do content fingerprinting and all of that stuff in the application layer? Do you do that inside network devices, in the transport layer, or do you do that in middleboxes and so on? And also things like, should it be in all network devices and network layers in all applications, or should it be in should specific parts of content processing happen in specific points and so on? And the reason it's important to figure out an answer to this question is that the right layer of abstraction at which you apply content-aware processing is key, because it enables content awareness to be general and be able to benefit a large class of applications and democratize the benefits across a large class of applications. And also a careful choice of the location and how you apply content awareness is important, because it is crucial to enable applications to evolve. And I'm going to show you some examples, hopefully, of how that could happen. And there's no one answer. I can't tell you, oh, always do it at the IP layer, always do it for packets, and always do it on routers. The answer may depend on the specific scenario you're looking at, so it requires a careful eye to that specific piece of detail. And again, there are included below on the slide are some examples of how we have picked the level of abstraction at which to apply content-aware networking. For example, our packet caches paper talks about how you do it on routers and how what could be done if you had support on routers. Refactor, a paper at Mobicom, talks about using content overhearing, again implemented at the IP layer. XIA, which is sort of more of a greenfield architecture, talks about elevating content as a first-class network entity, but having that operate alongside other entities such as services and hosts themselves. And the last strand of research, and this is one more boring piece of detail that I will quickly cover before getting into the meat of the talk, is what can you do if you had in-network content processing? And the reason this is interesting is that when you have in-network content-based functions, an example could be suppressing duplicate content. That's a contract that the service provides to higher layer, that the network provides to higher layer applications. Today, the contract the network provides is best effort delivery. Think of the future network with content processing as best effort delivery plus duplicate suppression. So in that new world where you have these kinds of content processing functions inside the network, some interesting questions arise, such as how would you do X in this new world, where X can be something traditional like routing or things like loss protection. So how do you do routing today, right? You have a graph, traffic needs to go in this graph between some entry point and some exit point, and the typical way to do this is to pick shortest path routing, something that minimizes the stress on bandwidth. But in a world where you have this network, the set of links and routers suppressing duplicate content, you would no longer go with shortest path routing. What you may desire in its place is minimum entropy routing, right? So you try to put traffic together as long as possible such that you have maximal ability to suppress duplicate content, even though that may cause you to take longer paths in terms of path length. Similarly, in terms of loss protection, people have talked ad nauseum about, oh, should you use FEC to protect video, for example, against losses, or site-like calls against losses? What should the level of redundancy be? But once you have in-network support for something like duplicate suppression, a whole new range of simple loss protection schemes become possible. And you can look at our NSCI paper from last year to do this. So this is another interesting thing. Once you have content awareness in the network, your whole view of how applications should be designed and whether classical things still make sense gets thrown out the window, and a whole set of new possibilities arise. Okay, so what I'm going to do in the rest of this talk is to pick a couple of these things, how to do fast network support and how to develop principled approaches to design to determine where to put content awareness, using a specific example of something called end-host redundancy elimination. This is a fairly old paper, but it kind of nicely synthesizes ideas from those strands of research that I described, at least 2 of those 3 strands of research that I described. And it is joint work with a bunch of people spread across UW Madison, MSR India, CMU, and UCSC. So before I go into the details, this is going to be probably a lot more technical than the first part of the talk. I want to just make sure there are no questions.
Question, anyone? I think we're good.
Okay. So so let me tell you what this is about by first starting and give me some context. Most of you here are aware of the move to the cloud. Everything is going into the cloud, right? So enterprises in particular are increasingly moving their services that they used to have locally into the cloud. Now the good thing for them is that they can consolidate management and they can outsource scaling and all of that stuff to the cloud. But the problem is what used to be local services within an enterprise are now remote. So all local area traffic is now wide area traffic. So it has implications for WAN usage costs, but also latency and the bandwidth available become affected. So it sort of impacts the performance and also cost. So the way to address this dilemma is to use the things called WAN Optimizers or redundancy elimination devices. Let's just use the term redundancy elimination to encompass all those sets of solutions. And essentially, what these devices do is that they basically suppress the redundancy in the traffic exchange across this wide area link between the enterprises and the remote data centers. They remove popular objects. They can remove partial content matches, headers, and there may be backups of things going on and so on. And in addition to WAN optimizers, there are also virtual redundancy elimination middle boxes that cloud providers are offering, or existing middle box vendors are offering for the cloud. And the good thing about these WAN optimizers is that it's protocol independent. All the traffic that you saw, irrespective of whether it is HTTP or email or whatever else, you should be able to use a single set of techniques to remove the redundancy and save on bandwidth cost and potentially also improve your bandwidth performance. And it works for static and dynamic. So typically the way these are done is you would have these middle boxes shown here that would each have a synchronized packet and cache. And this is your local data center, and this is your local enterprise, and this is your remote data center where you have now moved your applications or hosted your applications. When you want to send, let's say, responses from the data center back to the enterprise, you would look the the pieces of data that you're trying to send in this cache located in the data center. Some of these may see a hit. If a particular piece of content in your reply you want to send to your enterprise sees a hit, you replace that with a shim, and others would go in full. So in this case, a couple of them got replaced by shims, which are essentially memory addresses in the cache, and you send it over. The shims, when they reach the other end, are dereferenced with respect to the cache at the other end. You construct the full payload and send it over to the other end. So that's sort of how you save on the WAN bandwidth and potentially latency. So these chunks and the matches that you see can be for content as small as 32 bytes, and you can also do it for chunks of content. For example, 10 kilobytes worth of content. So these chunks can be arbitrarily sized. And typically these caches are sort of they are in memory, and they have a separate set of disk-based solutions for optimizing much larger chunks of data, like whole archival or backing up of data. And I'm not going to cover into the specific sort of details for that, but let's just focus on the in-memory systems for now. So this is sort of how WAN optimizers work, and this is sort of how they would use middleboxes to do WAN optimization. So the architectural question to ask here from the view of content-aware networking is this the right way to do content-aware networking? What are the downsides, for example, of using middleboxes? So the first problem is that most of this traffic is encrypted. So this is a bad thing for middleboxes. What this means is that each time you see an encrypted piece of data, either you just let it go without doing any compression, because you can't really look for matches against prior content because the data is encrypted, or you have to share keys with this middlebox appliance and try to do some reverse engineering and sort of essentially have a man in the middle attack kind of a thing happening to accommodate encryption. That's sort of architecturally unseen, and there is a significant potential for other attacks that may happen. The second problem also is that redundancy elimination works between these two middleboxes, but full payloads go to the actual end devices. So you don't really help out with devices like smartphones that have otherwise limited capability. So your RE benefits, redundancy elimination benefits, don't extend all the way to the endpoints. There are other interesting issues. There may be poor interactions with TCP. For example, one of the things that I had mentioned is that you could view those chunks as individual packets, and so you're removing little bytes out of the strings of bytes out of those packets. Now the problem is end-to-end TCP connections, because of this, have a very different view of what the congestion window should be, as opposed to what's happening inside the network. Because there's something inside the network that's using the available bandwidth in a completely different way than what the end-to-end TCP connection expects. On the other hand, if you split the TCP connection and did redundancy elimination across TCP chunks, the problem is you end up losing the end-to-end semantics of TCP. This is the classic problem with split connection approaches. And the final issue is cost. These middlebox appliances cost a lot. Okay. So in the rest of this talk, I'm going to make a case for figuring out the right way. I'm going to make a case that the right way to do redundancy elimination is to push it to the endpoints, do it between the servers in the data center and directly on endpoints. And I'm going to call this end-to-end RE or EndRE. And the first advantage is that it accommodates security and encryption more cleanly. You can do redundancy elimination before you encrypt, provided you do it at the right layer. It extends the benefits of redundancy elimination all the way to the endpoint, because you're actually carrying compressed data all the way to the end host, and then you decompress. Because you're saving bandwidth, you're sending fewer bytes over the radio link, coupled with some intelligent tricks for doing decoding of these encoded bits in a simplistic fashion on the end host devices. You can actually hope to get significant energy gains out of it. And provided you make the right choice for how to do this end-to-end redundancy elimination, you can have it operate just about TCP, such that what each TCP connection carries is actually compressed bytes. No further compression or optimization happens once the TCP sender sends the data. you can more cleanly accommodate all TCP issues such as packet losses or how the TCP congestion window evolves and so on. But the question that arises is it a good idea to do this? Yes, there are all these benefits, but really do they provide the same kind of bandwidth savings as middle boxes? And can you really do this on EndRE? On things like smartphones, each time you get an encoded packet, you have to decode it, you have to potentially look it up. That is expensive. It may take away bandwidth, battery from the smartphone. And the servers, the data center servers are already busy doing a lot of other computation. Now you're asking them to also do redundancy elimination. Is that possible? So those are the questions that I'm going to answer, and I'm going to say that provided you make suitable choices for content-aware networking and for how to implement it, you can meet these challenges fairly effectively. So let's look at the first question, bandwidth savings, and I'm going to talk about a bunch of measurement results that motivate the fact that there can be significant bandwidth savings you can achieve from doing this. So there are a variety of questions that come to mind with respect to the RE techniques in general, but I'm going to focus on one specific thing, and I'm going to refer to our Signetics paper from 2009 to get a broader sense of empirical insights into traffic redundancy. And I'm going to focus mainly on whether this end-to-end approach of doing redundancy elimination would compare well with a middle box, and try to derive some design principles for how to do this end-to-end redundancy elimination. Okay. All right. So for this, we collected a bunch of packet traces, almost 8 terabytes worth of data spread across 12 network links. One of them is in university, the other is 11 different enterprise access links, spanning nearly 50 days. And so this is sort of a very high level view of what we saw in the traffic for one of the enterprises. And what we see is that there's a significant variability in traffic composition. On some days HTTP is dominant, on other days it's not. Some other file sharing applications are dominant. And so because there is no one dominating protocol, it is good if you use a redundancy elimination technique that is protocol independent. And this immediately takes out of the picture things like web caches, which are very specific to HTTP traffic. You want something that doesn't need to know about the composition of the traffic in order to work well. So that automatically makes a case for protocol independent compression techniques. So we're going more to the point of whether end-to-end redundancy elimination is beneficial. We also looked at what are the properties of redundancy in traffic with respect to traffic shared between the same endpoints or shared across different flows, across endpoints, and so on. So we looked at the traffic exchange from a remote point to an enterprise, and among those we identify flows that are essentially flows of traffic going to different hosts in the enterprise, and we call that inter-host redundancy. Whenever there is something in common, we would call that inter-host redundancy. And within inter-host, you can imagine a variety of different classifications that the similarities across destinations, or the similarity could be across sources, or the similarity could be across different application endpoints. And furthermore, we also look at redundancy across different flows, but between the same pair of hosts. That we would call intra-host redundancy. The big question is which of these two dominates, and how much. Okay. All right. So, and again, here we can look at interflow and intraflow redundancy. So here is a quick overview of what we see across the different sites we measured. The first 3 are for the university links, and the last 3 are for the enterprises. The key thing is to notice the enterprise. Really, what we see is that the intra-host redundancy is significant, captured by the light blue and the dark blue bars, and this is very different from what we see in the university. There is a lot more commonality in the traffic within a flow or across flows involving the same pairs of hosts, as opposed to traffic shared across hosts or flows spanning multiple hosts or multiple sources of destinations. In particular, we see that the contribution is more than 75% for the enterprise links. For the university links, as you may imagine, there is a lot more diversity in the kinds of traffic university users are involved in, and we therefore see a much less concentration of this fashion.
This is a quick question.
Yeah.
So basically, this suggests that the same hosts are accessing the same data over and over again, right?
Right. So it's actually, absolutely. So it depends on what we mean by data over there.
Okay.
Is it the same object? Is it the same URL? So we look. This talk doesn't go into the details, but we looked at what exactly these matches are.
Right.
And it's things like often these matches are parts of packets. So things like some header of some HTTP page, or something else that was used to synthesize a bigger page. Those are the things that are accessed in common. And the pages are dynamic. So even though the entire page may be the same, it may not be cacheable, right? So none of those things are doing. So this analysis is sort of encompasses all of those possible causes.
So your unit of measurement is what, bytes or packets, or what? What do you mean by percentage here? So
bytes. These are the bytes that are repeated.
Okay.
So a match can be something that is a set of strings, contiguous set of strings inside a packet.
Okay. Thanks.
Okay. So another quick look at what sizes of caches we needed between the data center and the enterprise to extract, to be able to identify redundancies that I showed you on the previous slide. And again, here the key thing to take away is that we don't really need a really huge cache to get most of the matches. This is mainly for the in-memory cache that I'm talking about. I'm eliminating really large bulk downloads, really large flows. So on the order of something like 300 megabytes would be sufficient to capture most of the temporal matches that arise in the transfers between the data center and the enterprise. So this is not exactly the end-to-end video. It still doesn't reflect what happens between the endpoints, but this sort of gives you an upper bound on the total size of the cache that any endpoint may ever have to hold. And I'm going to return to this in the evaluation for EndRE shortly. Okay, so based on that, given the fact that there is some promise from doing end-to-end RE and you can get significant benefits, mainly because there seems to be a lot of redundancy traffic exchange within the same host. Let's now look at how to actually extract those benefits and how to systematically apply content aware networking such that we can extract those benefits. I think the key thing here is that there are a lot of different trade-offs that may arise. The first thing is the trade-off between being fast and effective versus processing load, right? So if you use some heavyweight mechanisms to identify as much redundancy as possible and use all the CPU power available at servers to identify this redundancy, that's great. You may identify a lot of redundancy, but that imposes significant processing load on the servers in the data center that takes away that CPU from the servers doing other interesting and more pertinent things in the data center. And our answer to this is to develop a new kind of RE technique that is both lightweight and tunable, so that if the server has free CPU, it can automatically tune the RE scheme and to be more effective, to spend more CPU resources on RE. The second trade-off is between again how much bandwidth reduction you are able to extract from RE versus the amount of memory you end up usurping away from the server. The more memory you use, the more matches you're likely to find because you have more states to look against. But that also takes away memory from the server's computation. And again, our ideas here are again carefully delineating how the memory is used and designing interesting new data cycles that allow the memory to be used in the most effective fashion. And the third set of trade-offs are, how do you deal with client-side limitations? If you completely throw them out the window, I don't care about what happens on a smartphone, then you can do a lot of interesting things that give you significant benefits in terms of bandwidth reduction, but your phone will die in maybe 10 minutes, right? So how do you reconcile these things? And again, here what we realize is that the servers are more powerful, so we want to offload as much of the redundancy elimination functionality as possible to the server and have the server essentially play a proxy for the client, and you will see what I mean by this shortly. Okay, so let's step back. Let's take a more in-depth look into it. Like I said, a packet comes in, and your idea is to quickly identify repeated content that may be as small as 32 bytes within this packet against the prior cache of data of all packets that you have seen in some time interval. Of course, you can identify all matches. Look at every 32 byte string and look at that, but that's impractical. It will take a lot of time, and you need a lot of memory for that. So the typical thing to do is to use a sampling-based approach, that you sample some of the portions of the packet and you look at those content samples in this big blue cache here. So to go into more detail, the way this works is first you fingerprint this content. And this is something I referred to earlier as an important thing in content networking. So design a fingerprinting scheme. And what a fingerprinting scheme does is it generates representative hooks into the content of the packet. Okay. And I'm going to talk about a new fingerprinting algorithm we developed called SAMPLEBYTE. Now, once you have these fingerprints for different points in the packet, you look up each of those fingerprints for a match in some sort of a data structure, and a match of the fingerprint means that there is some string of bytes in the packet that matches a string of bytes in an earlier packet. So you retrieve that, you encode that match, you take out the actual bytes in the packet, you encode it with respect to the memory address in this cache, and you send that along. Here again, there are a variety of different schemes you can use to do the matching and encoding, and we developed a modification to a scheme called max match that I will describe. Again, this sort of shows you how careful design of these content-aware processing schemes can lead to significant benefits. And there's another thing called chunk match that I won't have the time to get into, but I would be happy to refer you to our EndRE data to get to those details. Okay. So once you have found these matches, essentially, like I said, what you do is you take out the matched region and you encode the matched region with a memory address that indicates the position in this cache and a length that indicates the length of the matched region, and that's essentially what you end up sending as these little red blobs across the line. Once they get to the other point, you de-distance the memory address from the other cache and you reconstruct the origin byte. Notice that you assume here that the caches are synchronized, because if they are not, the memory addresses at the remote end may be something completely different. Okay. All right. So let's look at these fingerprinting. So one common way of doing fingerprints is a scheme called MODP. And essentially what you do here is you have a window, a fixed length window, something like, let's say, 32 bytes, that you compute a hash over that window for the entire length of the packet. So if the packet is 1500 bytes, roughly you end up with 1500 such hashes. You can use any hash function, but there is a specific kind of a function called a Rabin fingerprint. That's a specific hash function that you can implement much more simply using a small number of additions and multiplications. You don't have to recompute the hash function for every new window. Once you have these fingerprints, so roughly order 1500 fingerprints, you do something called value sampling. So basically you select a subset of fingerprints that all have, say, a fixed pattern in their last few bits. Let's say all of the fingerprints that have the last 4 bits as 0, 0, 0, 0. So that allows you to sample 1 in 4. So you get such representative fingerprints, and those become your fingerprints for the content. This is called value sampling. You basically sample the fingerprints based on the value of the data that it represents. The good part about value sampling and using MODP is that it is robust to small changes in content. If I put some small piece of little byte string inside this packet payload, or I remove a little byte string out of this packet payload, and this may often happen with dynamic personalized content, this scheme is robust against such small additions and deletions. You will still very likely pick the same set of fingerprints or a similar set of fingerprints for such changes. The problem here is that it is computationally expensive. You have to compute as many Rabin fingerprints almost as there are bytes in your packet. So it is computationally expensive. An alternative is something like a simple scheme like fixed, where what you do is every p byte you pick a marker, okay, and you compute a hash for some fixed region of the packet surrounding the marker, and then you use those hashes. This is simple. The selection criteria is very simple, and you can adapt this to load. If your server load is low, you can pick more markers. If it's high, you can pick fewer markers. But the problem is, if I insert some piece of content or delete some piece of content, the markers get thrown haywire. Okay, does that make sense? So what do we do now? So basically, we developed a scheme that enables us to get the adaptability of fixed fingerprinting with the robustness of the value sampling. So here's the algorithm. So what we do is we scan the packet and we choose a byte as a marker if some function of that value of that byte is 1. So let there be some function f that has mapped all byte values to 0 or 1. In this case, f of 0 is 1. So we choose that byte as a marker, and we then skip p over 2 bytes and start scanning again. F of 5 is also 1. It turns out, so we choose that as a marker. We skip over p over 2 bytes and start scanning again. We pick that marker and so on. Excuse me. So this gives us some selection of fingerprints. Now and we can derive this function f based on some greedy analysis over the data. We can kind of look at all traces, all packets exchanged to our enterprise and see what values of this function for different bytes give us the most optimal benefits in terms of redundancy. You can kind of train your scheme to derive the right f. And so the good thing about this scheme is that because it is based on value sampling, the value of the byte, it has the same benefits as MODP. It is still robust to additions or deletions of data, and because you're not computing hash functions for every little piece of data, it is tunable, and the selection criteria is extremely simple. You don't have to do hash computation order 1500 times to be able to select a fingerprint. Right? So it kind of combines the best of the two worlds. Okay, so just quickly going over matching and encoding. So like I said, there is some way of selecting the fingerprint. So we have selected our fingerprints, and then we look it up in the hash table. And if there is a match, we retrieve the packet or the chunk of data corresponding to the match and grow the match region byte by byte around the region captured by the fingerprint to identify the maximal match. So the challenge in these matching schemes is that you have to store all the payloads of the packet because that forms the basis for you to identify the redundancy. But you also have to keep this expensive fingerprint hash table to be able to look into that set of packet contents, and that turns out it takes up about 67% of the cache size. So if your packets are 2 gigabytes worth, then you almost have about 1.2 or 1.3 gigabytes worth of fingerprint. That's a significant amount of memory addition. So we developed a bunch of interesting tricks to overcome this. So instead of having a hash table with a load of about 50%, what we do is we simply use the first few bits of the fingerprint itself as a memory index into the hash table. And this simple trick of using you can kind of think of it as self-addressed content, right? So the content itself carries the memory address of where it is located. Immediately enables us to bring down the size of the metadata to a significantly smaller amount. So that's at the server side. We can play these tricks to bring down the impact of this fingerprint. So what happens on the client side? I haven't told you anything. The client side is simple. All the client side does is it maintains a simple FIFO log of the packets that it exchanged with the server. The server explicitly tells the client which packet to insert into its FIFO log, which packet to evict, and so on. In addition, the server also indicates explicitly whenever it is encoding content exactly which memory location in the client's cache it should read that content from. So the server controls everything. The client is extremely dumb. Okay? So what we have essentially done is push all the intelligence to the server. The client is very simple. At the server, we use this fast adaptive fingerprinting scheme coupled with this memory efficient way of storing content that gives us both the computation benefits and the memory benefits. Make sense? Mm-hmm. Okay. So now the question becomes, where do we implement this? there are a couple of different options for where to implement this at the server or at the client. We could put this at the IP layer, just before you have IP out in your TCP stack, you can have this stuff happening, or we could put it at the socket layer, right? Which would be above TCP but below the application. And we chose with the socket layer of the must mainly because it offers us a lot of benefits. It's a little harder to implement it there, but it offers a lot of architectural benefits. So the first is that it is better to deal with encryption. So the payload for packets that use things like SSL can be compressed before encryption. So it deals with HTTP traffic much more easily, as opposed to an IP layer implementation. You can have to completely give up on encrypted traffic. That's the right choice with respect to encryption. The other advantage of doing it at the socket layer is that in the case of the IP layer, the IP layer only knows about packets. So you're only compressing individual packets, so you're only taking away redundant bytes from individual packets. So the number of packets are not getting reduced, right? If you look at the number of round trip time, typically it's a function of the number of packets, not necessarily of the size of the packets always. But by implementing it at the socket layer, we have the opportunity of also reducing the number of packets, because what we hand down to the IP layer to segment into packets is basically a compressed chunk, and that allows us to get latency benefits as well. And we can also do a variety of other things. We don't always have to do EndRE at the socket layer. We can use other tricks like gzip. In some cases, as I will show you in the evaluation slide, just gzipping chunks of data ends up being more effective than EndRE. And the final thing is, remember I talked about these synchronized caches, the fact that the encoding cache and the decoding cache have to be synchronized, because the decoding cache has to know exactly where to read the data from. Well, often, if there is a loss, the caches can get desynchronized with respect to each other. The advantage of implementing our scheme above the TCP layer and in the socket layer is that the TCP layer automatically does packet retransmissions, and it provides an automatic way of keeping the caches synchronized for us. Okay. That's the final advantage that we get. So we end up with synchronized caches automatically, purely as a side effect of our TCP based implementation. All right. So let me talk quickly about sort of some of the benefits that we see. And so this is basically on using our traces that I described. We ran a bunch of traces against these things. Against various schemes that we designed. So the first thing here that I'm going to show you is how does our fingerprinting scheme work? Does it get us the claimed benefits of the ability to tune and sort of be lightweight while also offering significant benefits in terms of identifying redundancy? So the picture on the left hand side is the speed of our redundancy elimination scheme when we use a specific fingerprinting scheme. And the x-axis is the sampling period. In other words, how often you identify these fingerprints. So higher sampling period means actually less frequent fingerprints. So you can kind of think of it as once every 512 bytes you pick a fingerprint, or that would be the rightmost point here. So obviously, as your sampling becomes less frequent, your speed increases, except for MODP. Notice that the speed stays same, and the reason is MODP, if you remember, had to calculate a hash for every byte in the packet, right? And then it samples. And by coupling these two things tightly, you're not really gaining any flexibility with respect to being able to tune the overhead imposed by fingerprinting. On the other hand, PIX and MODP both scale linearly. As the fingerprinting becomes less frequent, you get better and better speed. So of course, the challenge is if you make fingerprinting less frequent, you also identify less redundancy. More frequent fingerprinting means there is a greater potential for identifying redundancy, and that's shown on the right hand side graph. As you make fingerprinting less frequent, what we see is that the amount of redundancy you can identify falls. In particular, if you look at fixed, while it is great in terms of scaling of speed, it is stuck at finding redundancy, mainly because it identifies specific chunks in the content, and small additions or deletions of content throw it off completely. It can identify very little redundancy. MODP does well, but it's not adaptable. Only SAMPLEBYTE gives you the best of both worlds. You can scale with respect to speed, scale in the computational overhead by choosing the appropriate sampling period, and also get suitable benefits in terms of identifying the traffic. So we also ran a bunch of experiments on understanding how much memory would it require, would a client require to use in this end-to-end redundancy elimination. So purely focusing on one pair of hosts, this graph kind of shows if that one pair of hosts used a particular cache size to communicate with each other, what bandwidth savings would they get. And you see that beyond about 10 megabytes between a pair of hosts, you don't get any additional significant benefits in bandwidth savings by adding much extra memory. And what does this look like across all the? This is just between a pair of hosts. The previous graph was between a pair of hosts. But if I look at all the hosts that a given host communicates with, what would the memory requirements look like? And if you look at the client, these are sort of devices inside the data center. The median client requires about 60 megabytes of memory. And if you look at servers, if you had something like 360 megabytes of memory for the server port, this captures all the active connections that the server may have at a given point in time with various clients. That amount of memory at the server is sufficient for it to do effective EndRE to various clients. Okay, so the memory impact is not too significant either, based on the choices we made. And again, we did a bunch of experiments of how much benefits this offers. I won't go into the details. This is sort of trace-based evaluation across all the sites. And essentially, if we just use in-memory middle boxes, they can identify more redundancy because they can also look at redundancy across hosts. End-to-end RE only identifies redundancy within a host, so we lose a little bit. But we can capture a lot of that by also using some other scheme to deal with large files, and something like a data-oriented transport scheme. You can kind of think of it as a peer-to-peer way of exchanging large files. We can retrieve a significant fraction of the benefits. But the key high-level point is that we come fairly close to the benefits of using a middle box simply from using end-to-end redundancy elimination. All right, what does it look like on end hosts? So this looks at the impact of decompression on end hosts, purely focusing on decompression. So what we do is we preload all pre-compressed chunks into the memory of a smartphone, and we repeatedly decompress those chunks by dereferencing into the smartphone's memory, and the Wi-Fi is turned off. So this doesn't look at Wi-Fi's impact. And so we looked at a couple of different alternatives. You can use zlib, something like gzip or whatever, to compress the chunks and decompress them, or we can use EndRE. So these two graphs kind of show energy and savings you get in bandwidth from using different schemes. Essentially, what you can see is that if we can use zlib, it seems fine, especially at large chunk sizes. But at small chunk sizes, especially at the size of an individual packet, the energy consumed by zlib becomes prohibitive. EndRE offers similar benefits as zlib, but at a significantly lower overall energy cost. Okay. All right. So what do the end-to-end savings on a mobile host look like? And now, so here what we do is we actually turn on the Wi-Fi on the device, actually send data to the device, use EndRE or whatever other scheme, and compare those schemes against not doing any kind of compression. So here what you see is, again, looking at zlib and EndRE against two different traces. If you apply it at the level of individual packets, if you apply zlib at the level of individual packets, you may actually lose out on energy. Although you are saving bandwidth, you lose out on energy just because decompression is expensive. EndRE, on the other hand, you can get significant benefits, and the energy and the bandwidth savings translate automatically into energy. So the high-level takeaway from this analysis is that it's not clear that EndRE is always the right choice. In particular, for very large chunks, you may actually want to just compress them, like use gzip. There's no necessary need to use EndRE. But for smaller chunks, you may actually want to use EndRE because it seems to be more energy efficient and gives you the necessary bandwidth savings as well. And so the way we adapted this in our scheme is, you remember we had the socket layer implementation. So the socket layer would buffer data, and it would wait for some fixed amount of time, or something like 10 kilobytes of data to be accumulated, whichever happens earlier. And once that happens, you use EndRE and send it off. But if there is some background transfer happening that is exchanging a large amount of bulk data, then you trigger zlib based schemes to compress that data. So that's sort of how we ended up deciding that would be the right way of doing compression. All right. So that's actually almost the end of my talk. So basically, what EndRE shows is some of the design patterns that I hinted at in our content aware networking work. Right? So essentially, we took the problem of, okay, people are using these middle boxes. How can we rethink what is the right way to do content aware networking? And our insight was based on measurements that it makes sense to start to move this out of the middle boxes into the end box. Mainly because with things like encryption and with things like mobile devices, this is going to be forced to happen anyway. And if you think about how we ended up designing this scheme, we had to make a careful choice on where to put the functionality, how much to do at the server versus the client, whether to do it at the IP layer or the socket layer and so on. In terms of lessons for how to do fast and effective content processing, again, sort of this division of labor hopefully came out. I hinted at the fact that you may have to coordinate what ends up happening where. So in this specific example, we ended up pushing a lot of the functionality to the server and doing very little on the client. And as you saw from the results, the new content fingerprinting scheme we developed, SAMPLEBYTE, proved crucial for the specific situation at hand for us. And so these design patterns gave us, significant processing speed. Server memory usage and processing was tunable, and we got significant bandwidth savings and energy savings from doing that. Okay, so that's about EndRE. I wanted to talk briefly about next steps or sort of what is out there, but I can end it as well right here and take questions, whatever suits you guys.
I think we can spend a few minutes.
Okay. So basically, I wanted to talk briefly about some other things that we've been thinking about and where I think this is headed. Obviously, everybody is talking about video. It's going to be everywhere. It's already everywhere, if not already, if not overwhelmingly so. So how do we take these lessons and apply them to video? Right. So this whole notion of fingerprinting, doing fast in-network processing, the equivalent in video is a perceptual fingerprint. Just like you compute a hash on a piece of content and that is somehow tied to the content, you need hash for a chunk of video that ties to the content inside the video. And you could, my feeling is that you could then use that as the basis for doing a variety of in-network video processing stuff. And we have some initial results in our CONEX paper that we can look at that hints at what these perceptual fingerprinting can look like. In terms of the second thread that I talked about, rethinking traditional schemes with a new lens. For video, I think one of the places to start this experiment is, how do you share videos? And the common way to do this today is through URLs. And the thing is that they are not always portable in the sense that not all URLs point to videos that play on all devices. So you need a more video-centric view of this world of URLs and what they should be. And there may be new approaches that you can develop for video that provide better loss protection for videos and improve quality of experience for videos. And again, I think if you take the specific domain at hand, video, and you kind of focus on what aspects make it different from regular content, you can apply those design threads and come up with interesting new sets of systems that work well for video. Okay, so I want to end here and take any questions that you guys may have about this talk.